Hello friends, today I'm going to talk to you about the effect of Young's modulus on the linear structural response of structures. So what is the effect of Young's modulus on any structure? So in a linear analysis, when we are doing, the Young's modulus is one of the important properties that decides its stiffness. So what are the effects it has on the structural response of structures? So let's have a look. So let us say you have a material, you have a structure, and what you do is that you keep the structures the same, the structure, the loads, the boundary conditions, everything you keep the same, and only thing you vary is the Young's modulus of the material. So in that case, what is the effect of the Young's modulus on the structure? So let's have a look at some of the properties of the structures. So introduction. So now the important thing here is that all the parts of the material, all the parts of the assembly are made by the same isotropic material, and we are performing a linear analysis. It can be a linear static analysis or it can be a linear modal analysis. So either way, some trends are observed, and those trends I will be making apparent in this video. So assumptions are one, the structure is linear. So the material has to be linear. So it cannot be non-linear for this analysis to hold true. So geometric nonlinearity, material nonlinearity, contact nonlinearity are not there. So this means that the deformation is small enough to be counted as small deformation, and also you see uh, the stress in the structure does not exceed the yield point at any location in the structure, and also there is no change in contact status in case multiple parts are there. So the second assumption we make is the material is isotropic. So the material has to be isotropic. If it is not isotropic, it complicates the issue. So for this video, I'll be limiting the discussion to material to structures made of material that is isotropic, like most metals and plastics. Third, only the Young's modulus is varied. We are not varying the Poisson's ratio. So if you change the Poisson's ratio, the structure will not behave the same. But here we are only varying the Young's modulus. So and with the variation in Young's modulus, what trends are observed that we are going to see. So other properties like the geometry, the Poisson's ratio, the loads, constraints, all etc. are kept constant. Now, the fifth point, there are no enforced non-zero displacements. So, if there are enforced non-zero displacements, then this analysis is not valid. Last point, there are no point masses. So, and of course, and the NB that is there. Here, I would like to say that there is no constraint on the number of parts in the assembly. So, it can be any number of parts, one part, two parts, three parts, thousand parts, million parts. It doesn't matter. So, ultimately, uh, if these points that I have mentioned in the assumptions, if those are satisfied, then this particular analysis holds true. So observation one, the stress induced in the structure is independent of the Young's modulus. So even so, let us say you have a structure made of steel, and it is showing a stress of 100 megapascals, maximum stress of 100 megapascals, or let us say 100 megapascals at a particular location. Now, even if you change the Young's modulus of the structure, let us say the Young's modulus of structure is 200 GPa. Instead, you make it, let us say, 30 GPa. Still, no change will be observed. Please note, this is only limited to Young's modulus. If you change the Poisson's ratio, then the stresses will change. And also, I'd like to tell you that let us say you are replacing steel with aluminum. So steel and aluminum have different Poisson's ratios, so the stresses will change. So the change in the stresses will be dependent upon the amount of difference in the Poisson's ratio. Now let me go to the next point. So the observation 2 is displacement is inversely proportional to the Young's modulus. So the structure, so as you increase the Young's modulus, the displacement will go on decreasing. This is expected because in any linear structure, the stiffness is directly proportional to the Young's modulus. So and the displacement is inversely proportional to the stiffness. So this means that the displacement will be inversely proportional to the Young's modulus, and that's exactly what we see here. So let us say you increase the Young's modulus, let us say from 70 megapascals, so from 70 gigapascals to 200 gigapascals, then the displacement is likely to decrease. Observation 3, the mode shape that we get in the modal analysis, that is independent of the Young's modulus in a linear modal analysis. This may be a little bit surprising to you, but it is true. Observation 4, so the National frequency is proportional to the square root of the Young's modulus of the material in a linear analysis. So if you take a national frequency